All right, welcome everyone to the 11th general body meeting of the 2020-2021 year. If you haven't yet, sign in at attendance. We'll have our normal raffle at the end of the meeting, and that's how you enter to win. So, like always, we are recording our meetings. We will have these slides available on our website in the archive, and also in the comment, the description of the YouTube video. There will be a link to the slides here. So any resources you want, you can get those after the meeting once we've posted those. ACM UC, you know by now, computer science and programming, open to all majors, all that good stuff. Code of conduct basically just means we're dedicated to a harassment-free experience for everyone. You can check out the full thing at our website. We also follow the UC code of conduct. So all that stuff, just be cool, make everyone feel welcome in our awesome little community here. Like I mentioned, we have our raffle that we've been doing at all of our meetings, at least for this semester, probably started last semester as well. Virtual meetings, no pizza. So as a way to give back to everyone, we're giving out gift cards if you sign in at attendance. And also, if you post a meme in the memes channel, you also, if you get the most reactions to that message in Discord, you can also win a gift card. So if you've got some original memes that you're making, especially about, computer science or compilers or anything else like that, I'm sure it'll get a lot of good reactions in Discord. So Slack and Discord are our main little online communities. So we have both of them are pretty similar. They have lots of different channels for different types of communication. They have desktop and mobile apps, all that good stuff. Code of conduct applies in both places. And if you're looking for some fun things to do on Discord, we have a Discord bot, or no, we have a trivia bot that we've been playing around with for a while now. We just added a question of the day bot that asks us some questions, and we just kind of chat in the general channel. And then we have office hours every Thursday at 8 o'clock. So that'll be right after this meeting. We'll just be hanging out there. So with that, we're going to jump right into our talk for tonight. Daniel and I will be giving a talk on compilers and how they work. So Daniel and I are in the compiler theory class this semester, and we've been very heavily focused on this project the whole semester. So we feel we have some good knowledge to share, hopefully.
Right. So obviously, for anyone who doesn't quite understand what a compiler is exactly, I'm just going to do a brief overview of what a compiler is and what it does. So a compiler is basically, just think of it as a translator. You can take any language, and it is the compiler's job to translate that language into another language. Now, primarily, compilers are intended to make the language simpler, closer to machine code, so that it can be executed. That's generally what you're going to be using a compiler for. It might be like C++ to C, for instance. But the idea is that it's going to make it simpler. So, you talk to your computer, you tell it exactly what to do, you write a program, and you tell the computer what actions you want it to take. And since your computer can't understand the code language that you're actually writing your program in, the compiler makes it so that the computer can do that. So as you can see, it's just going to take text and turn it into machine code. That's the gist of what a compiler does. Now, before we get into the rest of this, we thought it would be important to talk about the differences between a compiled language versus a interpreted language. So compiled languages are converted directly into machine code. that the CPU can execute. So you write your code, and then the compiler will, whenever you click run, the compiler has to do all this work to make it into machine code, and then the computer executes it. The idea is that all that compilation happens at one time, so there's kind of a lot of overhead when you run your program. But once it's all converted into machine code, when you're actually at runtime, it's going to be faster and a lot more efficient because it's already all been compiled. So getting back to that overhead, every time you run a program that is in a compiled language, it's going to require to be built. If you've ever heard the term build a program and then it actually runs, or rebuild, that is referring to it being compiled. So it has to be rebuilt every time you edit it. If you make any change at all to the code, then the compiler is going to take that as a opportunity to recompile the entire thing and then run it. And obviously once it runs, it'll be fast and efficient. This makes the testing take a little bit longer. If you're constantly if you're just changing a single variable or whatever, and you have to keep running it over and over again, you're going to have that overhead, especially if it's a really big code base. You're going to have to wait a few seconds for it to finish building or whatever. I don't know if anybody at co-ops has experienced that kind of overhead through a compiled language, because I know I have. We do C#, and it's this huge code base, and it takes a good 10 seconds just sitting there waiting for it to all compile. A good thing about another good thing besides the fast execution is that this isn't a good thing. It's platform dependent, meaning that depending on the platform, it needs to be compiled for that platform. And by platform, I mean computer architecture. So if you're talking about x86 or ARM, whatever the computer architecture is, it's going to compile differently. Thankfully, many compilers can figure out what your hardware is, and will compile it for you right there. You don't really have to think about that too much. But it's important to know that you can't just compile something on one machine and expect that same whatever the compiler spit out. You can't expect that to work directly on another machine unless the compiler takes all that into account. You'd have to recompile on the other machine. Examples of languages that are compiled are C and C++, Erlang, Haskell, Rust, Go, Swift. There's a lot more, but those are just some examples. Now, interpreted languages are different. They execute line by line. So when you run them, it'll just do one line, and that makes them slow when they're actually running. You don't have that overhead when you first click the run button or whatever. It doesn't have to build or anything like that. It's going to immediately begin reading the lines one at a time. But because it has to compile as it's reading the each and every line, that makes the execution itself slower. So these are platform independent, meaning that it doesn't really matter what you're running them on. It's always going to run the same way. That yields some benefits such as dynamic typing. There's other benefits too that go along with interpreted languages, which is nice. It generally allows the programs to be smaller. They can be more condensed and easier to understand. And examples of that are PHP, Ruby, and then the infamous Python. Kind of has all those qualities if you're familiar with Python at all. But yeah.
Right. Yeah. And so just kind of thinking again at how both of these, eventually you have to get from source code some kind of language that you type in to machine code. So both of these do that for your whole program, right? It's just the difference of compiled does the whole compilation all at once in bulk before you run it, and then you run it, and it doesn't have to do any of that work. But then interpreted, you're kind of compiling line by line as you go along. So it's doing some more work. as you go, and that's why it's slower execution. So some examples we already saw: C and C++, the actual compilers that they use. GCC, the GNU C compiler, was the original back in the day. I mean, I don't know what the first C compiler was, but that's one of the very popular ones. And then more recently, Clang, which Apple has heavily adopted. And last year, actually, or maybe it was the year before, I don't even remember. We had a talk from Christian Snyder, one of our ACM alum, and he gave a talk on V8, which is the compiler for JavaScript that runs in your browser to make sure your JavaScript code is running. And then Java is another compiled language. We have Java C, I would assume that's how you pronounce it, is the compiler that they have. And then Swift, also a compiler. They just you call it on the command line with Swift, so simple enough. And so basically for the rest of this talk, what we're going to do is go through how a compiler works, step by step, very generic, very kind of high level, but still getting into some of the details so that you understand. And so I've just laid out like a very basic language, like Python or C, but just very basic. So this is a super simplified version of C that we're going to be compiling for. Just like in C, you have an entry point. What the compiler is looking for that you're going to start your program at is the int main function. You can our fake language also handles functions, integers and floats, and it has a print function. Just included that to actually be able to see output, right? And then we have plus, minus, multiplication, division, mod, and assignment. So that's not, notice we don't have anything going on with Booleans, true or false, comparing if this is less than that or equal to that. This equal sign is just assigning a value to a variable, right? So let's see.
Okay, I think this one's mine.
Okay, yeah, that's you.
Okay, so this is just in pieces though. You might as well just do a couple of them. Yeah. So these are the general steps that the compiler takes. So of course you're going to give it an ASCII text file, basically just whatever code you have, just the language, with ASCII characters. And it's going to go through
and
this.
notice on that too that like no matter what language you're typing in, like .py, .c, .cpp, all of them have different file extensions, but at the base level they're still just ASCII text files. The compiler can read them all the same way.
Right. So your text file is going to go through a stage called lexical analysis, which basically just reads through your code. We'll talk about each of these stages in more detail in the coming slides, but basically it reads through your code and generates these tokens, which basically just cuts your code up into a bunch of little pieces that it can deal with. Then it will go through syntactic analysis, which will eventually output an abstract syntax tree or an AST, which basically kind of, well, in semantic analysis as well, kind of goes with this. Both of them kind of allow the structure of the code to make sense to the compiler. It has to understand how everything fits together. So it has to know that like there's a counter for a for loop and things like that. Then once the abstract syntax tree has been gone through, both of the syntactic analysis and the semantic analysis, that will go into some kind of intermediate representation. That's what that IR stands for. And that intermediate representation will be optimized, that the compiler will be able to read through that optimized intermediate representation better. Sometimes you can read that IR, like you could write it manually if you wanted to, but the idea is that that IR generation is like kind of the magic that happens with the semantic analysis, and it's closer to machine code. But then that machine code, uh, well, not machine code, but the IR will once again go through all these optimization steps, become more efficient, which makes it even less readable, honestly. But then it gets fed into this code generation step, which is where the compiler will actually convert your code to executable machine code, or ones and zeros, or bit code, or something very close to machine code that can be executed. I believe this. Yeah, this is mine as well. So for this example, this is our ASCII text file. This is what we would have written. Any of us would have written up this short program in this super simplified C language. Obviously, we define this add function that takes in 2 integers and just returns the addition of them. You have your entry point, which is the int main. Defining 3 variables, a, b, and c, assigning 1 to a, assigning 2 to b, adding them together, then assigning that result to c, using that built-in print function to print out what c would be, which obviously is 3. And then it's going to also print the result of the add function passed in a and negative a, which would just be 0. Yeah, and so the lexical analysis is that first step that the compiler takes. It's sometimes called the lexer or the scanner, and I prefer scanner just because it makes more sense and it just tells you what it does basically. And it's going to read through your ASCII text file character by character, literally every single character. But it will recognize groups of characters and create tokens out of them, or lexemes. Once again, I prefer tokens. That's just me. But yeah, so you have to define what all these different token types can be. You're going to have this table of different types that a token could potentially be. So you could have like operator add, operator minus, operator times. You could just do int, float, return. All of these things are special operators that the lexer has to know about when it's scanning through your code. So if it gets to a string, it'll probably read to the end of that string to see if it's like a specific keyword or something, such as return. So when it encounters an R, it's not just going to do something with that R right off the bat. It's going to keep going until it hits like a white space and say, oh, that's the word return. That's a keyword. If it's not return, if it's retur, then it'll probably assume that's a variable name. But the idea is that it's taking your code and just like splitting it up into meaningful chunks that it can actually utilize, such as like just even in that other section there, you've just got the left bracket, the right bracket, semicolon, comma. All those things are significant at this stage. Yep, cool. I believe this one's mine as well. Yeah. So that's the ASCII text on the left, and you can see how the lexer or the scanner will go through and divide it up into those different sections. So you can see just for that function there, starting at the very beginning, the first thing it's going to see is int. Then it's going to see add, and it's going to assign that like an ID because it's like a variable, a function name basically. And if you think about it, when you define a variable, you don't normally put a parenthesis right after it. So chances are down the road, it's going to see that parenthesis and say, oh, wait, this must be a function. But right now, it doesn't care about that. Right now, it's literally just breaking it up into these tokens that are going to be used later, because right now, the whole entire file as it isn't really helpful to the compiler. So it needs to make sense out of everything. All right. And then normally the way this works is you'll have some kind of scan function, which will, get that next token. Well, and you'll do something with those tokens as you go, or store them in a data structure or what have you. But that somewhere in your code, you'll probably have something that looks like while token dot type is not end of file, then you scan another token. That's kind of just a generic thing. So at the end of your ASCII file, it's obviously gonna read end of file. Once it returns that, then there's no more tokens to get, so you don't need to do any more scanning. But the idea is that somewhere in your code you'll have this scan function, which will get that next token and return it to that token variable.
All right, so now we've got this stream of tokens, just a giant list of things broken up kind of word by word in the program, right? So now we're going to do syntactic analysis, which is also called a parser. And so this is kind of, at least in our class, like we're building all this stuff from scratch, and this is the most significant portion of the project. Like this kind of houses everything else. This is like kind of the main structure that helps define how you call different things and where you do what. So it's a very essential part. And it kind of, like I said, validates the structure of the program. So like, for example, if you're declaring a variable, you know that should always come in this format. It has to have a type followed by an identifier, some kind of variable name. So if you have a type followed by a right curly brace, it's going to say, hey, this is a problem. This doesn't mean anything to me. So same thing with like an assignment statement. If you're assigning the value 1 to A, you know that the identifier is always going to be on the left, equal sign, and then some kind of expression. So it could be like 1 plus 1. That's still, all expressions evaluate to some value at the end. So like I said, it'll raise some kind of error if it finds some invalid syntax. That's like what you're seeing in your compilers when you are doing some classwork or whatever with C++, and you miss a semicolon, it'll tell you about that. And so now we're taking this stream of tokens, and here's our abstract syntax tree. So this is only a very small portion of it, and actually this is completely. Oh no, this is the same. Yeah. So so we can see our. Basically, this is our definition of a function. So we've only kind of highlighted this function portion, but basically you would have this kind of continuing upward, and it would go all the way to the root, like whatever your rootmost thing would be, like the root of the program. Like basically, if your program is just a list of functions, like that's kind of what the base of this tree would be. But we have a function, and so it recognizes, hey, a function needs to have a header and a body. And so the body is just, whatever is inside those curly braces as well as the curly braces themselves, right? So if something is missing the last curly brace, it's going to raise an error. So it's got to recognize each thing in its required elements, right? And so then in the header, it's going to be looking for a type, a name, parenthesis, a list of parameters, and another parenthesis, right? And so you can see it just kind of goes down at each level, getting more specific. So you have maybe a list, but then you say, okay, that list is going to be a parameter, a comma, or I mean, these are optional. So it could be no parameters, it could be one parameter, it could be parameter, a comma, another one, or comma, another one, comma, another one. But it has to kind of recognize what's valid and invalid. And then you keep going further down. Hey, the parameter consists of a type and an identifier as well. And so at the very base level, the leaves of this tree are the actual values themselves that we have scanned from the original file, right? So that's what the tokens actually are. All right, so now that we have this tree, what we can start doing is looking at the types of everything, seeing if they're valid, where they are. So you have stuff like your return type, your variables all have a type, And anything that goes on, maybe you're returning a value in your function body, that needs to have the proper type to match. So you're validating the meaning behind the code, not just looking at the structure, but more of the meaning. So verifying that types match, or they can be converted. So they don't have to be exactly right. You could, like in C++, you can say, hey, float f equals 1 plus 1. You know that 1 plus 1 is 2, or 2.0 in a float, but the compiler has to recognize, hey, that's a valid conversion. So it kind of has all of that figured out and built in. So you also want to verify that identifiers or the variable names have already been declared, or if you're declaring A and then you're declaring it again, that's not valid. So you want to throw an error there. And so there's a lot more that goes on in semantic analysis. But basically, that's the basics of it, is just figuring out more of the meaning behind the code and making sure types, everything is compatible with each other, right? And so here's an example of that. So in our program that we wrote, we have our, and I'm not going to show the abstract syntax tree here because this is much more simple. But you have your integers, A, B, and C. So it says, okay, A and 1 are both type integer, so that's compatible. That's good. B and 2 are both type integer. So then it's going to say, okay, so C is type integer. Now I want to check the right-hand side of this assignment expression or assignment statement. And so it will kind of recursively call all of what it needs to check, right? The parser will say, okay, here's an identifier, parenthesis, some parameters. All right, this is a valid function call. And then it will figure out what that function returns, right? So it returns an int, and then it says, okay, those two, C and the return of this add function, are both int. That's valid. And then finally, we have our, oh, right. And then also for our add function, it has types. Step back here. Yeah, so our add function has types int x and int y. So it accepts only 2 integers, so it will also check the types on those 2 variables. And then there's, of course, a lot more for printing, other stuff. Yeah.
All right. So once it's been
I guess
through,
I wanted to stop real
go ahead.
quick and just see if there's any questions. All right, then go.
There's no stupid questions either. Like this is like a super in-depth look at compilers, kind of. I mean, yeah, we're just scratching the surface, but it's and it's not super important when you're just writing code. But it is kind of nice. I mean, I'm definitely interested in compilers because you're using them all the time, and it's like I just have this desire to know what exactly is running, what's going on behind the scenes that's allowing my code to just work on a computer magically like that. So if there's any just general questions as well about just compilers, period, it doesn't need to be about anything specific we're talking about, but we'll do our best to answer any questions. You can always put them in the chat. But anyway, once you've got the semantic and syntactic analysis done, then you are at this part where the intermediate representation that the compiler is going to use is generated. So yeah, you take that abstract syntax tree, and then it's going to come out as this intermediate representation. So this intermediate representation is pretty much going to look very similar to assembly. If you've never seen assembly, just know that it's really close to machine code, so it's super hard to just write things right off the bat in assembly or in an IR. Of course, you can learn it, and you can figure it out, but it's definitely not ideal. And you're going to have to do things like register allocation. Um, that's more on the side of computer engineering. So if you've taken computer architecture classes like that, um, that's the kind of stuff you'll be dealing with this IR. Um, so like I said, you can create your own intermediate representation language, or you could use one like LLVM. Um, LLVM, we've been working with it a ton in our class, and it's basically just a handy way. It's like a replacement for GCC. It's just a handy way to create an intermediate representation and make use of that. And going into that would be a whole lot of unnecessary details for the purposes of this talk, um, but you can see here how just those two statements, C equals add AB and print C, are converted into this intermediate representation that would look something like this. Of course, it depends on what you're using, um, but it's got these percent signs before the variables to say that they are variables. It's saying call because it's going to be calling a function that returns a 32-bit integer. Named add. Um, that's that at sign. Also, is that what makes it global, Brandon? In your
I think that's
this
what
one?
he said
Okay.
last week. Yeah, yeah.
Yeah. So yeah, the add sign is telling it that add is a global function that can be used anywhere. Once again, all this syntactical stuff at this point just depends on what intermediate representation you're using. That this is just LLVM syntax. Um, you can see there's a 32-bit integer A and a 32-bit integer B, and then it's calling another thing called print that has a return type of void, and it takes in a 32-bit integer.
Yeah, those are like the simplest ones I could find
Yeah.
that match to our things, because these
Yeah.
IR statements get very complicated very
Yeah.
fast. So
Once again, they're just super ugly, and if you don't have something handy like LLVM, you have to do all this register allocation and keep track of what register is holding what, which is absolutely awful. Whereas LLVM takes care of all that for you and lets you, um, whenever you assign a variable, it will it gives you these infinite virtual registers basically, whereas most computer architectures have a varying number of registers. Um, but LLVM just makes that really simple and takes care of all that register allocation
yeah, I
for
mean,
you.
if you want to go back to the 40s and slide in your punch card with code and do everything manually in very low level binary, then go ahead. But
Yeah, that's basically that. It's just gross. So thankfully we have that step to help us along. But anyway, once you've got that intermediate representation, I guess you don't have to go through any optimizations at all. But the idea is that it becomes fast and you can uh, compile it quickly or run it quickly, I should say. So it's part of the compiler's job to optimize this intermediate representation before it sends it off to the computer to become binary or bit code or something very, very close to machine code that can be executed. So it's going to take that IR and look for patterns within it that can be simplified into more simple expressions. Now, they might not necessarily be more simple for us to read. Um, you know, it like we might however way we wrote our program, we're going to assume that that is kind of the way we envision it in our heads. But a computer can take those statements and look at them and be like, wait, this is just this. Like this is just simpler, such as x minus x. Whenever it sees x minus x, it's not going to bother performing that calculation. It's just going to see that and be like, well, wait, that's always going to be 0. Or x minus 0 is always going to be x. Those are just really simple optimizations, but there's really nice optimizations like loop unrolling, where instead of doing all this branching, once again, if you're familiar with computer architecture, you have to do those branch instructions, which causes stalls and everything. But if you eliminate that branching and just unroll all of the loops, which are really nice and pretty for us to view and for us to write instead of just repeating something over and over again, but a computer doesn't really care about the loop. It's going to make it quicker by unrolling all of like whatever is in the loop. Is there anything else on this slide? I'm not sure. Oh yeah. So yeah, there's no reason to do all these calculations at execution time, because we want the execution to be fast. That's the whole point of the compiled languages and everything. So we're just gonna like figure out all these patterns and eliminate all that extra overhead at compile time, since they're always going to be the same regardless of where you're at in the code. And so you can see right there, instead of branching off to that function, sending in both of those variables, finding out what negative a is, and doing all that extra stuff, it's just going to be like, well, wait, a and negative a is just going to end up returning. That's just going to be 0. I think that would be a little bit more of an advanced operation, just because they're being sent into a function, and it's not just a minus a. But the idea is still there. It's going to make the execution time a whole lot faster if you do lots of optimizations.
All right, so we're on to the last stage already, man. So optimization, you're taking an intermediate form and outputting an intermediate form that's just more efficient. So in the end here, we have our intermediate representation. And so code generation is basically as we've gone along, we've gotten more and more complicated, right? So we started out human readable source code. I wrote this, I understand everything that's going on, all the way to here. We are going to basically, the code generation is mapping your intermediate representation to each individual CPU instruction specific to your machine. So whether you have a Intel x86 processor, or you're on your iPhone, which is running on a custom ARM processor, or Raspberry Pi also has ARM, all that. They're going to be slightly different CPU instructions way down at the binary level. So all the good compilers these days, they have to handle so many different possible cases. And so again, it takes out the complexity for even for us as the compiler writers. If you have a tool like LLVM, is a tool that you have that intermediate form that you have to get it to that intermediate form, but once you have it there, LLVM will just figure out what's the best way to get it to the CPU instructions, so that you don't have to know every single possible CPU instruction. And again, so we've been getting more complex as we go down here. So this conversion from this intermediate form to actual executable is easier than doing it between two other things, right? Or just between the abstract syntax tree and executable, because your IR is already so close to assembly. So as we saw in that previous one, it's already very similar to assembly. It's got the registers and the two operands to like the call has two things following it, right? So it's all very similar to assembly. So it's much easier to get to assembly. And so then in the end, you're gonna get a binary executable file. So when you run GCC or G++ to compile your C code on your computer, unless you are compiling and you're getting a bunch of .o files and then you output to your executable, usually if you're just doing one file, right, it's just gonna by default create a.out file, and that is your executable. So you can just call that on the command line and it will execute. There's nothing else that any tools or anything has to do to get it into a form that's closer to what the machine understands. It's already there, right? And so like we said, if you're using LLVM, there's built-in tools to compile the IR to assembly, and then you can use some other tool to convert it from assembly to an actual executable. So it would still be in assembly, it would still be in some file like a .o or .s file. But in the end, you just want it straight executable. On Windows, it could be like a .exe file. It's your executable. And so that's it. You get your a.out file or whatever you name it, call it from the command line, and there's our output from our program that we wrote. 3 and 0. That's it. That's all we got for for all that work.
We got a question in the chat from Piyush. I'll take that. I'll take this one. Unless you have something you want to chime in. But so the intermediate representation, is it going to be different for different architectures? It depends on it really, like the differences with the intermediate representation is what you're writing the or whatever. What would you call LLVM? A compiler infrastructure,
It's called
basically. I think it's a
he calls
compiler.
it an IR language. It
Okay.
does in the documentation. It does have like a language
Okay, because I know
documentation. So it is
LLVM,
considered a
yeah,
language.
they call it like a compiler infrastructure, basically. But yeah, so the IR isn't different for different architectures. I guess you could have IRs that are specific to a particular architecture, but any good IR is going to work for any architecture. So like LLVM, you could
Yeah,
write
that's the whole benefit. Yeah.
right. That's the entire benefit of it. It's like assembly, so it's not very hard to make it into something specific to a machine. But usually they're set up so that however you write them, it'll figure out what machine. Like actually, LLVM has these special files um, that actually allow um, architecture like developers, like people that are working on ARM and stuff. It allows them to put to incorporate these files that say, "Hey, ARM has 32 registers, and this is and this is what each one is written as, and everything." Um, so these intermediate representation like languages are given that information about um, many different architectures, and so when they do actually do the code generation, they'll convert the code properly for that whatever architectures they have in their system, or whatever one you're on, I should say.
Okay.
Um,
Yeah, I was just wondering because it said 32 and I was wondering if it's 32-bit and it's for the 32-bit computer architecture. But
right.
okay, that makes sense.
And then is memory allocation important in the IR? Technically, yes. But like LLVM, for instance, which is kind of the new age IR, like I said, they kind of do that. They do this thing where you just get infinite registers, basically, but they're just virtual registers. So the IR, like LLVM, will take care of all that stuff, where it has all those infinite registers. It will do the allocations for you as it needs to.
Okay, thanks.
hmm
All right. So we're here at the end. So yeah, any other questions? We just kind of want to have a quick summary here at the end and have some time for any questions. Because there's a lot of stuff going on here, and there's so much further you could dive into each one of these. I mean, my parser, I just finished today my semantic analysis, and so basically how I have them split is like the scanner is its own file, but then most of the structure of the parser and type checking is in the same file in the parser. My one file is like 1,200 lines of code today. So it's a lot of stuff. So any questions at all from anyone?
Yeah, see, I wrote my parser, and then I haven't looked at it for 3 weeks. So the semantic analysis is going to be something for me. I kind of need to I need to polish that anyway. But yeah.
Oh man, how long did it take to make this much of the compiler?
I don't. I didn't
That's
put a whole
tough.
lot of time into it. I mean, at least to get the general parser down. because I think like the scanner doesn't take very much time at all. That's kind of just an evening thing. I mean, as long I think it helps to understand it from a conceptual level. Makes it a lot easier to write it. Yeah, there's no assignments for this class, for the compiler theory class. It's literally make a compiler. He gives you that syntax. He tells you all of the rules that need to go into the parser. And he gives you test programs to run and stuff.
Yeah, and I'll say just this last 7 days, I spent most of my days working on this type checking. So yeah, it's a lot of work. But that's why I signed up for the class. I'm enjoying it. So what part of the compiler is the hardest to make so far? Well, I know that this IR generation is going to be probably the most lengthy for me. Just
I mean,
how
knowing about it is scary.
Yeah, we had to give a presentation last week on like very general, high level about LLVM to our class, and just like learning that much about it, we were like, oh boy, this is going to be a jam-packed 3 weeks that we have to do this. So yeah, I think the parser is very important. So like, especially just having done the scanning so far, getting to the parser was like the hardest learning curve. But now I think the IR generation with LLVM is going to be the hardest. Let's see.
Oh, I do want to make a clarification for anyone who was curious, because it was bugging the crap out of me the other day. LLVM stands for low level virtual machine, but now it's so much more than that. It does a lot more than just that. So really, it
Doesn't
just
mean
goes.
anything.
Yeah, it doesn't really mean anything. Like, it might as well just be
Just
like
letters.
a proper noun. Yeah, it's just LLVM. Like, that's just the compiler infrastructure. So don't worry about it meaning low level virtual machine, because that's what it was intended to be, but it's grown into a whole lot more than just that. Let's see. Is it a compulsory CS course? Or
Oh no, it's an elective.
yeah, it's an elective. Yeah. Open source compilers that you guys refer to.
I mean, all of the big languages are
They're
so
massive.
complex
Yeah,
that
yeah.
there's no way that we can learn anything from it. Like, yeah, like all of these individual pieces, like we're only scratching the surface and like doing a basic implementation for our language. Like, there's probably the bulk of like expertise that lots of people who do this for a living, they get so deep into the optimizations and like how you can make it more efficient. Like Christian talked last year at the V8 compiler. He talked a lot about the crazy optimizations that they do to make it the fastest JavaScript compiler. So but yeah, we've been looking at some compilers from previous students who've taken the class, just to like even just doing our research on LLVM, we were like, what's the most simple use case here? Like, how what do you even do with all of this stuff? There's so much stuff that you can use in the libraries, so it's hard to pick out what exactly is useful at the very minimum case.
Yeah, I honestly think for the average individual, it's better to just understand compilers at the level that we've just explained it. Like, and just leave it at that. Like, if you want to torture
Yeah.
yourself, go in depth. But the idea, like, just understanding what's happening behind the scenes, especially that stuff in the beginning with like the scanner and the parser and the type checking and all that. That's the stuff that really affects you in a way, because you get those error messages from the parser. That's where they're coming from. As far as all the intermediate representation, code generation stuff, that's just the nitty gritty behind the scenes. the behind the scenes stuff. But it is interesting to see how it all works out.
Yeah. So last thing here, like we mentioned, we're in this compiler theory and practice class. So if you're interested in learning more, I'd suggest taking it. It's weird because he mentioned like you need strong programming experience, like know all these data structures, but we haven't really used complex data structures in the class. It's just like creating some of your own classes and structures when you need them. Otherwise, like my part, like all the type checking and stuff has just been a ton of if else, uh, and using like a class I made. Like other than that, it's not the most complicated, but once you get to that higher level of like the whole compiler as a whole, it gets complicated, right?
Maybe if you maybe if you go into more depth in compiler theory, then you might need data structures because of like efficient memory allocation and stuff like that.
Oh
You
yeah.
data structures for that.
Mhm.
But yeah, at this level, I don't think we need to go into that much depth.
Yeah. So yeah, like we've mentioned, we are building a compiler from scratch. We've learned a lot for sure. You don't necessarily get a whole lot from the lectures. Like a lot of it is just going into it yourself, how you're building it, making decisions on how you're going to build it. It's all very, very cool programming experience. And one thing I realized that to simplify this presentation, I didn't even mention recursive descent. That's a part of the parser. Understanding how the parser works is, if you're interested, you can Google recursive descent parsing. That's kind of the next thing I'd look into. But yeah, other than that, I guess, Daniel, do you have anything else you want to say?
I don't think so. I think that's pretty much covered everything. I would say that with compiler theory, Brandon's right. You don't get a whole lot out of the lectures. Honestly, I mean they're interesting, but as far as helping you on your compiler, not a whole lot. But the before if you're interested in taking the class, just be aware that you are going to have to get your hands dirty. I wouldn't say you need to necessarily be a strong programmer, but you have to be able to sit down for hours and like run your hands through your hair, like that, and just kind of be confused and then figure it out in the long run. So if you could do that, then you can handle the class.
Yeah, awesome. All right. Well, thank you all for coming. We're gonna wrap up. Let me stop this recording and